Up to now, we have talked about algorithms that learn given whatever features you provide. And we've talked about how you can engineer by hand features that do a better job of giving you the results that you want. In the second half of the course, we're going to be talking more and more about algorithms that find their own features that best solve a problem. And one of the reasons that support vector machines are such a standard part of data science and machine learning are that they can use kernel functions to learn features that best solve your problem. And oftentimes this is called the kernel trick because of the way that we can write the objective function for a support vector machine algorithm in terms of the dot product between vectors, and we'll see how that can help us solve problems that were previously intractable. So consider this data set where you have one class of points sandwiched between the other class of points. And can you solve this with a linear separator? No, of course not, as you hopefully remember from our discussions of VC dimension. But if we move into 2 dimensions, suddenly this becomes linearly separable. This isn't a new idea. There's actually a very nice novel about how moving to an additional dimension can change the way you think about the world. So if you're interested in mathematics literature and mathematics history, I strongly encourage you to take a look at Abbott's Flatland. And just as in that book, when people discover an additional dimension, they now can see problems and solve problems that they had no idea existed before. Adding a 3rd dimension can cause problems that were not linearly separable in dimensions to be separable in additional dimensions. So let's say that you wanted to solve this kind of circular problem where you have one class that forms a circle around the other. Is clearly not a linearly separable problem, but just as before we could go from 1 dimension to 2 dimensions and make something linearly separable, we can do that again by basically adding in an additional dimension that represents the radius of the points. And so now we're adding an additional dimension that is essentially computing how far away from the center a data point is, and once we add that, the red points now are separated on this additional dimension. But this is what we could have done for feature engineering, where we've talked about hand-engineered features, and we've talked about how adding an additional dimension as a function of the previous dimensions can help us solve a problem, but this is the kind of stuff we did in feature engineering. What's so special about support vector machines? The neat thing about support vector machines is its objective function. And so the objective function has a term that is essentially a dot product. Recall that the intuition of a dot product is basically how much does xi look like xj. And the generalization of that is a kernel function. And so a kernel is defined as a function that takes 2 examples and returns a real number. Mercer's theorem says that this is equivalent to taking the dot product between 2 points in some potentially infinite vector representation phi. So our job is now to find kernel functions that encode similarity in some way that allows us to escape from our initial feature representation. And because of the way that the objective function is specified for a support vector machine, the only additional computational cost that we incur is computing the kernel. So let's say that we have a polynomial kernel of the form x times x prime plus c raised to some d power. This allows us to solve problems like the XOR problem. And so if you then look at one of the induced dimensions, square root of 2 x1 x2 and square root of 2 x1, these are one of the additional dimensions that the kernel introduces, you now have a linear separator that can divide your data. Another kernel you can use is what's called the Gaussian kernel, which encodes how far apart 2 data points are. When you actually plot what this looks like when you use a Gaussian kernel is that you have something that looks a lot like k-nearest neighbors, but smooth. And so you now have a decision boundary that hugs the positive examples, but still has all of the nice properties of SVMs that it can handle slack variables and things like that. But this isn't just useful for continuous representations. For example, sometimes we have discrete inputs like sentences. And so here you can do things like compute a tree kernel. And so let's say that you have two sentences, a dog and a cat. A tree kernel can look at the tree representation of those sentences and count up how many structures match. And in this case, we have matching in these sentences a noun phrase going to a determiner and a noun, a determiner going to a, and so this is matched on the cat side, and then you also have a noun phrase headed by some noun with a as a determiner. And so 3 out of the 5 linguistic structures match, so that you can say these sentences or phrases are relatively similar. And these are very simple sentences, but for more complicated sentences, this gives you a nice interpretation of how syntactically similar these sentences are. This is useful for things like machine translation, where given some new sentence that you want to translate, you want to find examples similar to what you've translated before. So at this point you may ask, what does this do to the complexity of the algorithm, both in terms of finding a solution from data and to the theoretical guarantees? We won't talk about either of these in much detail, but in terms of the computational complexity, you can still use something that looks a lot like SGD, but you have to do some bookkeeping to make sure that you keep the constraints satisfied. Take a look at Understanding Machine Learning, and they give examples of algorithms both with kernels and without kernels. One of the great things about using the kernel trick is that the algorithm doesn't change very much. If you want to learn more about how kernels change the Rademacher bounds of the algorithm, there's some somewhat tricky details about whether the matrix representation of the kernel is positive, semi-definite, or not. And this actually turns out to be rather important, and you need to make sure that your kernel, when represented as a matrix, doesn't have too large of a trace. That being said, kernels are a great extension to support vector machines, which are a standard starting technique for data analysis and classification. So what I'd like to talk about now is something a little bit more practical. How do you actually use kernels when classifying data? And we'll look at some examples from sklearn. So calling a support vector machine classifier with a particular kernel is quite easy. And so here's an example of calling a support vector machine. Take a look at the sklearn documentation and see all of the kernels available. We'll talk about a couple of the kernels available, but explore on your own. Although we'll mostly talk about sklearn, there are many other packages out there that allow you to use kernels or to even define your own. So first, let's take a look at this data set where a linear kernel just won't work. And so if you use a polynomial kernel, such as we talked about before for solving the XOR problem, and just use d equals 1, that doesn't get you anything, obviously. That is essentially just a linear classifier. With d equals 2, you can see that the decision boundary is creating a curved path through the data that's doing a better job of capturing this relationship. Going up to d equal 3 makes it look more like an ellipse, but it's still capturing these data inside the ellipse. Now let's take a look at other kernels, such as the Gaussian kernel that we talked about before, which is using a notion of distance between data points, and thus is kind of like a smooth version of k-nearest neighbors. And the larger gamma is, the more local similarity matters. So if we use gamma equals 2, we get something that looks a lot like the d equals 3 polynomial kernel answer. But as we increase the gamma to 100, we get a nearly perfect fit of our data. Here is a simpler data set, And if we use gamma equals 1, this looks pretty much like a linear decision boundary. As we go to gamma equals 10, it's curving around a little bit, but still looks fairly linear. With gamma equals 100, it's very closely following the low-level differences between positive and negative examples and is taking a very curvy course through the data. But you can overdo it if we now go up to gamma equals 1,000. We now essentially have k nearest neighbors with k a very low value, and it's basically not generalizing very much. It's only looking at, in the training set, what is the closest example. So you can definitely overfit on your training data with kernels, so you need to be careful about that. So while kernels can give you great training error, you need to be careful that you're generalizing well. Take a look at what the decision boundary looks like if you can, and always have a held out data set so that you can see if you have overfit on your training data. So to recap, this concludes our discussion of support vector machines. We'll be using a lot of these ideas as we move forward. It's a workhorse of machine learning algorithms, and although it's not as popular as it once was, it's still very important, and you should know how it works, since a lot of the ideas, like loss functions, margin separability, and kernels, we'll see again and again in many other algorithms. And in particular, the kernel trick, which allowed us to learn feature representations that best solve our problem, will come up again later when we're using deep learning techniques to learn representations of our data that best solve our problems.